Okay, let's look at one last case of a Thevenin equivalent circuit. And in this particular example, we'll cover the last type that we haven't seen yet, which is a network that has only dependent sources. So when you have that situation, you have a slightly different procedure that you follow. Okay? There is no voltage or current source in the Thevenin equivalent. There'll only be a resistance. Okay, and to solve it, you can't solve these circuits that have only dependent sources the way that they are. So you either apply a current source across the terminals and then solve for the voltage, or apply a voltage and solve for the current. Okay, and then remember that you can you pick a basic value for the voltage, like 1 volt. And then that is the V, and then once you solve for I, you can then solve for R Thevenin. Okay, so let's look at how that works. So what I've done is I've chosen to put in a current source, and so I need to know what VAB is. So I can use any of the methods that I've encountered so far, and I think what I'm going to do is use nodal analysis. So what I'll do is I'll select a ground node, and then I'll label all of the node voltages. We'll just call this one Vx for simplicity. This can be V1, and this could be V2, or you could call it VAB, I guess, right? Because once we've solved the voltage at V1, well, that's the same as the voltage across the terminals. Okay, so now let's start with nodal analysis. And I'll start by doing KCL at node 1. Okay, I don't think that we really need to do the node at Vx, because you'll see there's a better way to do that. Okay, so I guess I forgot, when we're doing nodal analysis here, we want to label all of our currents. So I'm going to label mine just like that. Okay, and we'll say that going in is positive. Okay, so we'll start over here. This is going to be V2 minus V1 over 2K. And this is going in, this is plus. And that's Vx over 1K. And then finally going out is V1 at a higher potential than Vx. So V1 minus Vx over 1K. All of that is equal to 0. And when you simplify that, you're going to get 4Vx minus 3V1 plus V2 equals 0. Okay, let's do KCL at V2 now. And we have 1. We'll say that going in is positive, so 1 milliamp. And everything else is going out of the node. So that's going to be minus V2 minus V1 over 2K, and minus V2 over 1K. And now I can simplify that and put it in the same order as this equation here. And I get minus 3V2 plus V1. Oops, that's not right. So plus V1 minus 3V2 equals negative 2. Okay, so I have from those nodal equations, I have two equations and two unknowns. Now, I could do nodal analysis here on Vx. I could look at the current going through this thing here, but probably the easiest way to approach solving for Vx is to recognize that it's really just a voltage division, right? I know the voltage across both of the resistors, and so I could use voltage division to solve for that. So let's do that. Voltage division. We'll say that Vx equals V1 times 1K over 1K plus 1K, or 2K. Okay, the K's cancel, and we get Vx is equal to 1/2 of V1. Okay, so now what we can do is plug this into this equation here, and when we do that, we'll then end up with a system of two equations with two unknowns. Okay, so let's go ahead and do that. So we'll say we're going to plug voltage division solution into this equation. So that's 4 times 1/2 V1 minus 3V1 plus V2 equals 0. Okay, so then we get what? 2V1 minus 3V1, so we get minus V1 is equal to minus V2. And so you can see then that V1 is equal to V2. So now we don't really even have to do a system of equations here. We can just plug into either one of these and solve for both V1 and V2. So let's plug into this one, and we'll just plug in V2. So V1 equals V2. So we get V2. Let me I'll use the same color here. We're going to get V2 minus 3V2 equals minus 2, or minus 2V2 equals minus 2, or V2 equals 1. So we now have V2, and remember that V2 is equal to VAB, same thing. So now we've solved for the voltage, and we have the current, which we chose. So we get R Thevenin is equal to V over I, which is equal to 1 volt over 1 milliamp. Okay, and that will then equal 1,000 or 1K ohms. Okay, so our Thevenin equivalent then looks something like this. Okay, and that's how you solve problems like that. There's a little bit more arithmetic because you almost can't avoid having to do either a mesh equation or some nodal equations, but in the end the Thevenin equivalent is extremely simple to solve. Okay?